In my last video, I built the salt electrolysis cell for my workshop, a device that can use electricity to deconstruct and reconstruct matter at the chemical level. I'd like to investigate how it's able to do this, but as I went deeper into trying to understand how it works, I fell into a bit of a rabbit hole, and have now built multiple other electrochemical devices to retrace some of the steps of the humans who discovered electrochemistry. In order to understand my electrolysis cell, I'd like to focus on one particularly mysterious type of reaction, crucial to all life on Earth, that always happens to show up whenever anything interesting is happening. Oxidation and reduction, aka the flow of electrons from one chemical to another. This happens in all life, but also in many minerals, like this iron, sitting abandoned in the woods, rusting. This slowly corroding metal may seem far removed from my electrolysis cell, but in essence the two are one and the same, and according to the famous chemist Michael Faraday, one is simply the extension of the other. I believe by understanding rust, we'll be better able to understand the electrolysis cell. One trick with rust that was crucial to the discovery of electrochemistry is that it's spontaneous, meaning that it happens naturally at ambient temperature. If instead of letting the metal rust naturally, I place iron filings in the flame of this blowtorch, I can accelerate the oxidation process quite a bit and create spouts of fireworks as the iron burns in air, producing iron oxide. This is literally iron burning. So is that what rust is? Does metal just spontaneously smolder at ambient temperature with some invisible fire? If that is the case, why would metal spontaneously smolder at ambient temperature, but not other stuff, like charcoal or wood or all those other things we know react with oxygen? Also, why does iron only rust sometimes? Why does leaving metal outside make it rust, but keeping it inside prevents rust? After all, there's obviously oxygen both inside and outside. As it turns out, oxygen in the air actually doesn't react with iron at room temperature. Effectively, the activation energy of iron burning in air is just too high for it to happen on its own, just like with charcoal. The spontaneous oxidation of metal has to be enabled by something else. In this case, it turns out it's the water in air. The difference a little water makes can be astonishing. This copper adze was deposited in the foundation of Hatshepsut's temple in Egypt, nearly 3,500 years ago. And because of its arid environment, it is hardly oxidized at all in the thousands of years since it was made. Whereas the mysterious ancient Greek Antikythera mechanism was found in a shipwreck underwater, and was so horribly corroded that it was impossible to tell how it worked, until it was extensively x-rayed to reveal the remnants of the gears beneath all of the built-up oxides. As it turns out, not only is water important, but also an impurity in that water. We've seen that metal kept near salt water, like at the ocean, corrodes much faster than metal near fresh water. And if the water is perfectly pure, the metal will seemingly not rust at all, or at least very little. Now the mystery is deepened. We've gone from a fairly obvious reaction between iron and air to a complex reaction that seems to require iron, air, water, and even salt. It's clear salt water is crucial here. In some way, it's enabling our metal's invisible fire, just like a spark enables regular fire. But if water is silently burning metal all around us, can we tap into that flame? Does it release energy the way a normal flame does? A voltmeter can reveal the invisible by tapping into the flow of electrons that has always been there. As you can see, by dipping a hunk of iron connected to a voltmeter into the saltwater solution, with the other side of the meter attached to an inert graphite rod in the solution, the voltage meter wiggles as some of the electrons the iron is releasing pass through it, demonstrating a weak electrical charge is present. We're actually successfully tapping into the energy of iron rusting. Electricity appears to be flowing from the metal into the water, causing this reaction, while oxygen joins to the metal and causes the rust that we see. This makes me wonder what the connection is between the water that receives electricity from the metal and the oxygen that rusts the metal. To explore this principle further, we should test if this property is specific to iron, or if other metals work too. For example, this piece of zinc is much more reactive than iron, and when I submerge it in the salt water, not only is a voltage produced, but a significantly higher voltage is produced. Zinc is what Galvani used in his frog experiment, and this zinc and salt water combination is what Alessandro Volta used to create the first voltaic cell, which led to the invention of the battery. To see if voltage increases with the metal's reactivity, or if zinc is just an exception, we can use an even more reactive metal, like this magnesium. The voltage is going even higher, which makes it seem as though more reactive metals really will make higher voltages, and are more willing to donate electrons to water. But this raises another question. What if instead of making the metal more reactive, we swap out the salt water for something more reactive? If salt water corrodes metal, could a more corrosive substance increase the voltage as well? For example, would an acid in solution, like vinegar, be able to pull electrons from the metal more strongly than salt water? Evidently, vinegar and magnesium produce more voltage than the salt water and magnesium did. But the reaction is so much more vigorous that we can see the metal froths with gas that's bubbling out of solution. Along with this, the metal erodes away and dissolves instead of becoming covered in oxides. This mystery gas raises a lot of questions. Figuring out what it is will be crucial to understanding what's actually happening here. Let's start by dropping a piece of magnesium into vinegar without the circuit. We can see the gas is still being released, so it would appear this is a spontaneous reaction. We're not turning it on by connecting the circuit. It's just happening, just like how the iron would rust, whether or not we connected a circuit to it. Now the question is, what actually is this mystery gas that metals release when they're dissolved in acids? Luckily, Henry Cavendish answered that question for us in the 1760s by lighting the gas on fire. Don't try this at home, as doing this before exhausting all the air inside the flask could easily lead to violent combustion. When done properly, however, a small, almost imperceptible flame appears. The flame is small because the vinegar is dilute, so not much gas is being released. I can make the flame more perceptible by using it to light a piece of paper on fire, or by using more concentrated reagents to make more gas. Michael Faraday liked to perform this demonstration for his students in lectures, and he called it the philosopher's candle. 8 years before Faraday was even born, in 1783, after Henry Cavendish had determined that only water was produced as exhaust by this gas being burnt, another natural philosopher, the famous Antoine Lavoisier, termed the flammable gas hydrogen, meaning water generator in Greek. Now the question is whether hydrogen is released only by the acid, or if salt water oxidizing metal will release hydrogen as well. Perhaps it has been this whole time, we just haven't noticed because the reaction rates have been too slow to produce the frothing we noticed in the very reactive combination of magnesium and vinegar. To answer this question, I'm going to need to make a battery. This battery will combine multiple voltaic cells in a row, in this case just 4, and I'm going to make it as easy to modify as possible so we can experiment with different things. One thing I was curious about while researching this project is where Alessandro Volta got the idea to combine multiple voltaic cells in series, as it seems kind of random, but is also very important for using and understanding electrochemistry. As it turns out, the idea of a battery predates Volta's battery, and Benjamin Franklin actually coined the term in reference to his experiments on static electricity. Static charges in Franklin's time were stored in capacitors called Leyden jars. It was found by combining multiple of these charged jars that the resultant charge is stronger than any one of the individual jars. Just like the more cannons you have in an army's artillery battery, the more powerful that battery. Hopefully, by combining multiple saltwater cells into a battery, I'll be able to elicit a more powerful reaction from them. And in that way, we might just be able to see hydrogen. Hydrogen is crucial, because if we see it, then we'll know what's happening in rust is that water is being broken apart. As in our cell with magnesium, sodium chloride table salt, water, and graphite, water is the only one of those things that contains hydrogen. If we see hydrogen, then it's reasonable to assume it's coming from water. We can't make that assumption as easily with the vinegar cell, because the acetic acid in vinegar also contains hydrogen. This battery will be a way of isolating variables by limiting the hydrogen in the reaction to only one reagent, the water. One interesting thing this would point to if it is the case that the saltwater cell produces hydrogen, meaning that the water is being broken apart by the electricity it receives from the metal, is that the oxygen atoms we see built up on the metal as oxides wouldn't have to come from the oxygen in air, but could instead be the shattered remains of a broken water molecule. The hydrogen, having bubbled away, would leave behind a hydroxide, aka the water's oxygen atom bound to its one remaining hydrogen. This negatively charged molecule could easily bond with the now positively charged metal atoms that have donated their electrons to the hydrogen. Though every oxidation reaction is different depending on the context and reactivity of the chemicals involved, this would mean that in the case of the magnesium I've been using, all the oxides we see as corrosion on the metal come not from the oxygen in the air, but the oxygen from a broken water molecule. If it is true that this reaction hinges on the decomposition of water, then we can begin to see why Faraday thought the spontaneous oxidation of metal was so similar to electrolysis. Faraday coined the term electrolysis, meaning to break a chemical apart with electricity, which appears to be exactly what's happening to the water in our voltaic cell. If we think back to our abandoned iron in the woods, rusting away, we now have a picture of it transmitting electricity through the water and the air around it, cleaving that water into bits, and then rejoining the water's remnants to its chemical structure, creating a new compound we call rust. The only missing piece is the role of that crucial impurity of some kind of salt. To gain the increased electrical potential of the full battery, all of the individual cells need to be connected in series, meaning the graphite cathode of one cell needs to connect to the magnesium anode of the next cell, effectively allowing the electrons from one cell to push on the next. Only the electrons that pass from the magnesium through the graphite to the water will be useful, and all of the electrons that go straight from the magnesium into the water will effectively be an inefficiency in our design. In such a simple battery, nothing really prevents that from happening, and in a future video, I'd like to experiment with the advancements in battery technology that fixed that problem. But for now, it will have to do. For context, my battery here only has a few cells, whereas those used by Faraday and Humphrey Davy and others of their time would typically have hundreds, sometimes even thousands of cells. In his experimental researches on electricity, Faraday's go-to voltaic trough, as they were called, was a battery of 10 cells. However, he would frequently use many of these troughs simultaneously, and typically would use more than 10, meaning over 100 cells was normal for Faraday. That said, they used zinc. By using the more reactive magnesium, my smaller battery can reach similar voltages to a zinc battery, more or less 2 times its size, depending on the oxidizing agent used. With the finishing touches added, my battery is complete. Let's connect it to the voltmeter to see if it works. A much higher voltage is being produced, as the electrical potential of each cell is added to the last. Despite the fact that this is still just magnesium and salt water, by combining multiple cells, it's producing a higher voltage, higher even than we were able to achieve using corrosive acid. By shorting the battery and connecting one end to the other, we can see a copious amount of frothing. This is the hydrogen we've been waiting for, and this proves that the metal's oxidation is actually breaking apart water. With everything we've seen so far, we can begin to put together an idea of where the energy is coming from in this oxidation reaction. As we saw earlier, metals like iron can burn, just like fuel. Magnesium can burn as well, and being more reactive than iron, it actually burns a lot easier. However, when we react the metal with salt water, the water which can't normally burn receives electricity from the metal and releases hydrogen, which does burn. In exchange, the magnesium is turned into magnesium oxide, which doesn't burn, but rather, as we see here, just incandesces in the intense heat without reacting. We're physically seeing the energy that was once in the metal being transferred to the water. We call this reduction, and in this case, the metal is our reducing agent, aka our fuel, or really more accurately, our electron donor. All these words are effectively synonyms in most cases. But if all that's required for an oxidation and reduction reaction is a source of electrons, What if instead of using a reactive metal's natural tendency to donate electrons, as we have been, we instead charge an inert conductor with electrons artificially? Will it still break water apart? Now that we have a battery, we have a source of electrons to play with, so I'll quickly throw together a device to experiment with. All it needs is a stand and 2 electrodes, but because the electrode material is so crucial here, I'm going to make them adjustable and easy to exchange for other materials. I'm basing this device loosely off of this electrolysis cell utilized by Sir Humphrey Davy, Faraday's predecessor at the Royal Institute of London, for similar experiments. By using inert electrodes made of graphite, or metals of very low reactivity, in my case titanium, but in Humphrey Davy's or Faraday's the go-to metal was platinum or silver, we can change the properties of the cell in a crucial way. Those highly noble metals won't oxidize readily, and thus won't produce electricity spontaneously. And unlike in a regular voltaic cell, the metal won't be acting as a reagent in the reaction, only the electrons passing through it. As you can imagine, this ability to react chemicals with electrons alone makes some strange phenomena possible, many of which we'll have to wait for later videos in this series to go into. However, for now, we can use this trick to try to explore the mysterious role of salts in our oxidation reduction reactions. I'm going to use the device to run electricity through a solution of potassium hydroxide. Pure water isn't conductive, so this will let us run electricity through the water. Bubbling at the electrodes makes it clear water is still being broken apart, but unlike the voltaic cell, where the water forms hydroxide and binds to the metal, here, the water's hydroxide itself is oxidized, converting it into oxygen gas as the positive lead pulls away its electrons. Much like the voltaic cell, hydrogen is still being reduced and is receiving electrons. However, this time, it's bubbling from the negative lead, unlike in the voltaic cell, where the hydrogen is supposed to come from the positive lead. This is electrolysis in its simplest form, the decomposition of water. Faraday termed this type of decomposition, where a compound is broken apart into its constituents, such as water into hydrogen and oxygen, primary decomposition. It's the electrons alone causing the change we see in the substance. Primary decomposition doesn't just affect the water, but also affects the salt dissolved in the water. One of the salts that Faraday determined to undergo primary decomposition was sodium sulfate, sometimes called sal mirabilis. The salt of sodium hydroxide and sulfuric acid, which I've just made in a double displacement reaction between sodium carbonate, known as soda ash, and magnesium sulfate, known as Epsom salt. This awfully pretty reaction precipitates magnesium carbonate and will lead to some contaminant of carbonate salts in my yield of sodium sulfate solution, but it really won't matter that much for this. After filtering, I split the solution between 2 vials and added a small amount of pH indicator dye, which shows the solution to be mildly alkaline, possibly due to the carbonate contaminant. A wick placed between the vials creates a path for molecules to travel back and forth, while still preventing the liquid in the vials from just mixing with each other. Right now they're the same, but by applying a voltage to the cell, a change begins to take place. This time-lapse shows that the vial with the positive electrode becomes less alkaline, as though it's reacting with an acid, whereas the vial with the negative electrode remains alkaline, if not becoming more so. This is the primary decomposition of sodium sulfate, which here was prematurely halted by a chilly breeze causing the sodium sulfate to crystallize. This decomposition produces sulfuric acid in the acidic vial, and sodium hydroxide in the alkaline vial, which are the acid and alkali necessary to make sodium sulfate. One of electrolysis's most interesting applications is this ability to take apart salts, which as you can imagine can really be very convenient and enabled all sorts of discoveries. A quick note, as you can see the importance of wearing gloves and goggles even with simple experiments like this, as the spill from either of these vials could irritate the skin, if not cause burns, and you certainly don't want either in your eyes. What's crucial here is that this reaction shows the movement of molecules in the electrolytic cell, and more than that, demonstrates that salt isn't acting as one substance, but two, a negative substance, in this case sulfate anions, that travel to the positive vial, and a positive substance, in this case sodium cations, that travel to the negative vial. Faraday termed these charge-carrying molecules ions, from the Greek word for go, because he determined that the ability of these charged molecules to move from one place to another was what enabled water to conduct electricity. He found that any substance that could render water conductive could also be broken apart into ions by electrolysis, and he termed these substances electrolytes. As you can tell, Faraday's names really stuck around. What's interesting is that these same electrolytes are also the substances that enable water to oxidize reactive metals, like magnesium, zinc, and iron. As we saw earlier, the battery releases hydrogen from the graphite rod. This means water is breaking apart there. For the battery to work, the hydroxide ion released when this water is cleaved apart needs to be able to travel to bond with the magnesium ions on the surface of the magnesium on the other side of the cell. It's the electrolytes that enable this travel. This finally brings us back to my original electrolysis cell. Well, I've managed to take up so much time getting here that I'm afraid I'll have to, yet again, save actually using it for another video. Well, what we just saw was what Faraday termed a primary decomposition. My salt electrolysis cell was meant for what he called secondary decompositions. These are more complex, and will have their own video. But as a teaser, they are essentially what happens when the constituents of water produced by the primary reaction are able to react with the constituents of salt also produced in the primary reaction. This leads to a secondary reaction, or even a number of secondary reactions. It only works for certain types of salt, but when it does, entirely new compounds are made. The most common secondary reaction is that of common table salt, which can be used to create bleach, as well as multiple other related compounds, through the oxidation of its chlorine anion by the hydroxide ions produced by the water. Mine, as many clever viewers guessed, is meant to produce sodium chlorate, a potent oxidizer with many exciting applications. That said, I'm going to end this video here. Thanks for sticking with me. I really enjoyed making it, and I haven't been able to look at rust the same way since. I really hope it's been enjoyable for you too. If you liked this video, please subscribe, and if you think you might know someone who would like it, sharing it can really go a long ways. Your feedback is really valuable to me, so if you have any questions, comments, corrections, or ideas to improve these videos, please feel free to comment below. This one took far longer than I expected, but it shouldn't be too long till the next video, as I've got a number of other projects in the works, at least a few of which will likely be posted before the next installment of this series. Thanks for watching, and bye!